Well, for many computational computer solutions and also sometimes even doing things by hand, it's useful to have the Schrodinger equation in a dimensionless form. And I'll introduce how we do that and then talk about some of the pros and cons of it in this segment. Uh, so just to make things clear, I'm going to look at a particular system, but the process is identical in even more complicated systems. Here I'm going to be looking simply at hydrogen atom or a hydrogenic ion, one electron systems. Right? And in addition, I'm going to be also using the CGS Gaussian units. And I can tell that from looking at this Hamiltonian because there's no 1 over 4 pi epsilon naught here. So that tells me immediately that that was in Gaussian units. Uh, and for these systems, we've seen the Hamiltonian operator is h bar squared over 2 mu times the Laplacian operator, and this expression in Gaussian units now. And then the Schrodinger equation is just this, that operator operating on the wave function equals E psi. And for our purposes, I can just use the Laplacian and Cartesian coordinates here, and I'll leave this r as just r for the most part. But remember, in Cartesian system, r is the square root of x squared plus y squared plus z squared. Uh, First thing I'll do is look at the case where I now want to change into atomic units. And you can view that in two ways. One is I can express a distance x anywhere as a number, x bar, uh, and the unit, which would be the Bohr, or the Bohr radius. And likewise, all these others are length measurements, and so they likewise, since they're length measurements, I have the numerical value of it, and then the unit, in this case, the Bohr. Now, the way I like to look at it is, in fact, is has some dimensions, but if I divide it by a naught, then I get a dimensionless x. So a dimensionless x is an x that has, whatever units, centimeters, whatever, but divide that by the Bohr radius, and that gives me in whatever units you're using, and so that gives me a dimensionless value for x. Okay? Likewise, the reduced mass, I can write that in a dimensionless form, if you like. But really, in atomic units, the reduced mass, or any mass, is a multiple of the number of electron masses. Okay? So the fundamental unit in atomic units is the electron mass, or another way you could look at it is this mu bar is the mass of the object, the reduced mass of the object, divided by the mass of an electron to give a dimensionless mass. Energy can be done the similar way. There, the fundamental scale is the Hartree. So if you can view this as writing the energy in Hartrees, it would be the unit here. would be the unit, or is this expression, remember? It's essentially twice the Rydberg, so 27.2 electron volts if you use electron volts. And then this E bar is the numerical part. Or alternatively, again, the way I like to look at it, I have a dimensionless energy. It's the energy of the object scaled to this Hartree energy. Well, if I plug all of those into this equation up here, I get this. So for mu, I substitute mu bar times me. For x, I substitute a naught x bar. For y, I substitute a naught y bar. For z, a naught z bar. For r up here, I substitute a naught r bar, and then for energy, e bar h, Hartree energy, e sub h. And pretty obviously, all these in brackets, I've got an a naught squared in each term, so I can pull that outside. And these others I can keep the same. I'll just write out what the Hartree energy is here it was given here, so I just plug that in. Oh, and then I'll fess up to the fact, as we've seen, for a single electron system, the reduced mass is effectively the mass of the electron, and so the reduced mass dimensionless mu bar is a number so close to 1 that we might as well just make it 1. And then what I'll do to get to this next, so I made that 1 for an electron, and I'll multiply through by m naught a naught squared and divide by h bar squared. So it gets rid of h bar squared, a naught squared, and me on this term. And to do that, I had to multiply by me e naught squared, h bar squared over the whole thing. So in particular, I have to multiply this term by it. And I also have to multiply this term here. There's the Hartree, me e to the 4th h bar squared. And I multiply through by me a naught squared over h bar squared. And then finally, let's see what I did. Oh, I substituted the Bohr radius. A naught is really 0.5 angstroms, but that came from this set of constants here. So I'll plug that in. Everywhere there's an A naught. I had some cancellation. I didn't mention that, but there's a cancellation of one of the A naughts here. Nothing else really canceled on that. And so now then, everywhere there's an A naught, up here, I'm going to substitute this value. And so this term becomes me over h bar squared, that was still there, a naught squared. Well, one of them cancels, so it's just a naught. So I just plug in a naught here, which is h bar squared me over e squared. And then the rest of the stuff, z, e squared, and r bar stayed the same. This term, I get me over h bar squared. That was still there. I get a naught squared, so that's my this parentheses, substituting this for a naught here. And then finally I look and multiply it times e to the 4th h bar squared. And if you look at these term by term, you'll see that I've got an e squared on bottom, which will cancel this one. I get an m and an me, cancel the h bar squared. So everything goes away here except for z, and that's just a number. R bar squared, r bar. And then this term over here, I've got an m on top, and then a squared m on bottom. So all of the m sub e's go out. I've got an e squared here, but it's squared, so it will cancel with this e to the 4th on top. And I've got a h bar squared. It's squared, so I got h bar to the 4th, but that'll cancel with these two h bar squareds on the bottom. And so all together then, I get an equation for psi in which each one of these coefficients are dimensionless. Now, in general, there's some numerical values, but whatever they are, they're small in scale. Well, lots of times people prefer to write the Schrodinger equation in a dimensionless form like this and solve for the wave function. That has certain advantages, particularly as we'll see. To solve any realistic problems, you have to go to the computers and have a program that solves the Schrodinger equation numerically for you, or you do it using a computer. And if you have these large numbers like h bar squared is 10 to the minus 64, and then you wind up maybe squaring that again in the midst of a computation, and you can very rapidly find situations on computers where you have underflows and overflows. And you may have encountered this a few times on a calculator, depending on how high a quality of calculator you have. But sometimes you'll put two numbers in and divide them, and it'll get zero, and you know that the answer in the back of the book is not zero. It's a very small number, but and you've reached an underflow on your calculator. Okay? So dimensionless Schrodinger equation is virtually the starting place of all computational work in quantum chemistry, computational chemistry, quantum chemistry. They will make a non-dimensionless dimensionless form for their system, and then use that as the starting place so that they have less likelihood of getting overflows and underflows and having their software computation crash. Uh, Now, I don't know what software you use here, but this dimensionless Schrodinger equation is actually what's solved in the guts of the program for programs like Gaussian and games, and I don't know. There must be there's probably getting something close to 100 or so of these computational chemistry programs that calculate energy levels and spectra and that sort of stuff. But the two that I'm probably most familiar with are Gaussian and games. But I'm sure every time I go back and look at these, they seem to be that there's additional ones. So, uh, well, uh, if you ever get into a position where maybe you want to go to work for one of these companies that issue these software, or maybe you work someplace where they have to extend those in some fashion, then it's important that you use these dimensionless forms of the Schrodinger equation. Very, very often nowadays, you can either input form dimensionlessly, or they will make you choose your sets of units that you want to work in, and it will do that the very first thing. But ultimately, what they solve is the dimensionless form in the guts of these computer programs. There is a downside to doing a dimensionless form for the Schrodinger equation. It's really a danger. Very, very often, if you keep all the constants as constants and work through with dimensions, well, you can check intermediate results, at least for dimensional consistency, to make sure the units are right all the way through. And certainly at the end, you should be able, if you're computing a length and you compute it and it didn't come out to have meters for the result, then you knew that something was wrong because it wasn't dimensionally correct. When you use these dimensionless forms and solve those, you're able to do very, very little of this dimensional analysis to check results. And so that's one of the dangers of the system. But usually, people that work with it so much, they're confident in their basic equations and their abilities, and they double check, and so they carry on with these dimensionless forms. Maybe sometimes a little too brashly, but nonetheless they do it.